Hi, I'm David, and I'm excited to present our work on relating adversarially robust generalization to flat minima and the robust loss surface here at ICCV. And this is joint work with my advisors, Matthias Hein and Bernd Schiele. I will start with a short 2-minute overview. We consider robustness against adversarial examples of various adversarial training variants. Training on adversarial examples has recently been shown to be very effective in improving robustness. However, adversarial training is prone to robust overfitting, as shown here. While cross-entropy loss on adversarial examples during training in light blue reduces continuously, the robust loss on test examples in dark blue actually increases after roughly 60 epochs or 40% of training. We hypothesized that this overfitting is caused by converging to increasingly sharp minima in the robust loss landscape with respect to changes in the model's weights. We measure this by computing the change in robust loss when applying small random weight perturbations. This is shown in red, where a higher value indicates a larger change in robust loss corresponding to a sharper minimum. Clearly, sharpness increases significantly during robust overfitting. This becomes particularly apparent when plotting robust loss on test examples on the y-axis directly against our computed robust flatness measure on the x-axis. Here, early epochs are drawn in blue, while later epochs are shown in red. In the second half of training, a clear, nearly linear relationship between test robustness and flatness can be seen. And this indicates a strong relationship between robust overfitting and converging to sharp minima. Our paper shows that this relationship extends across many different adversarial training variants as shown here. Again, the y-axis shows the robustness as cross-entropy loss on adversarial examples, and the x-axis measures flatness in terms of change in robust loss. More robust models show better flatness, that is, lower values on the x-axis. This includes well-known approaches such as traits in orange or AT-AWP in violet. But it also includes very simple regularizers, such as weight clipping in blue or simple weight decay in green. Furthermore, approaches explicitly optimizing flatness, such as entropy SGD in light orange, also improve robustness when applied on top of adversarial training. More details can be found online in our paper, or just stick around for the remainder of the talk. The talk is structured as follows. I will briefly introduce adversarial training and the problem of robust overfitting. Then I will highlight our contributions and discuss our proposed flatness measure in detail. And afterwards, I will go through all of our experiments, showing a clear relationship between robustness and flatness. So in this paper, we care about robustness against adversarial examples, meaning imperceptibly perturbed images causing misclassification. This is illustrated here using the by now famous Panda image, which is misclassified as gibbon with high confidence after adding this adversarial noise shown in the middle. Such adversarial examples can be computed in practice by simply maximizing the cross-entropy loss L between prediction F and the true label Y, as shown on the bottom. To this end, the noise delta is usually constrained in its L infinity norm, as highlighted in red, in order to make sure that the noise is imperceptible. Cross-entropy loss computed on adversarial examples is referred to as a robust loss and serves as our primary measure of robustness. We will also use robust loss to quantify flatness later on. As defense against such adversarial examples, adversarial training has received considerable attention. Essentially, adversarial examples are generated on the fly during training, and this can be written as a min-max optimization problem as shown here, where W are the model's weights to be learned, and this essentially means that adversarial training directly minimizes robust loss. Adversarial training, however, exhibits severe robust overfitting. As shown here in dark blue, the robust loss on test examples does not continuously decrease throughout training, but starts to increase very sharply around 30% of the epochs. This is despite the robust loss on training examples continuously decreasing in light blue. We also highlight that robust loss increases significantly not only for misclassified, but also for correctly classified test examples in rows. The impact of robust overfitting can, of course, also be shown in terms of the test error on adversarial examples, the so-called robust test error. Here, robust overfitting increases the test error on adversarial examples significantly, and therefore early stopping is commonly employed as simple but effective strategy to avoid robust overfitting. We think that robust overfitting and poor robust generalization are partly caused by converging to sharp minima during training, and this is illustrated here, where the black curve demonstrates the loss surface on adversarial examples of the training examples. As the optimal weights on the test examples, however, in red, do not necessarily coincide with the found weights on the training examples during training, the sharp minimum generally causes a larger generalization gap, and this is made explicit here using the dotted red and black lines. In practice, this leads to poor robustness on the test set, and it indicates that finding flatter minima is desirable in general. Therefore, we first propose a scale-invariant flatness measure to empirically measure flatness or sharpness of the found minimum. And then in a series of experiments, we demonstrate that flatness and robustness are strongly related. This does not only hold throughout training, so for robust overfitting, but also across hyperparameters and even across different adversarial training variants. To measure flatness in a robust loss surface, we consider random weight perturbations as shown here. The blue curve shows how the robust loss changes in a random direction in weight space for our adversarial training baseline. Now we fix a local neighborhood around the found weights and measure the robust loss with and without weight perturbation. And we will see later that the definition of this neighborhood is important to make the measure comparable across models. Flatness is then measured as the difference between the robust loss with perturbed weights, L tilde, and without L. Averaging over multiple random directions, flatness basically expresses the expected change in robust loss given small changes in the weight space. Higher values correspond to sharper minima, while lower values indicate flatter ones. This is made explicit here, where the first term is the expected change over weight perturbations, and the second term is the reference robust loss without weight perturbations. In practice, we sample 10 random weight perturbations to compute the first term, and the second term additionally makes sure that the measure is comparable across models, which may exhibit different robustness levels to start with. Moreover, our measure is invariant to scaling of the weights. This too is very important for comparison across models. For example, using stronger weight decay during training generally leads to a smaller scale in terms of the weights without necessarily impacting cross-entropy loss or robustness. To avoid having to choose differently sized neighborhoods for different models, the neighborhood B is defined on a relative basis per layer, as highlighted here in red. And so if the weights are scaled up or down for a particular layer, the neighborhood adapts accordingly. First, we consider robust flatness throughout training of our adversarial training baseline on Cypher 10 using a ResNet 18. Again, we show test and train robust loss in dark and light blue. At the same time, we show robust flatness in red. As can be seen, robust flatness increases quickly when overfitting starts around epoch 60 or 40% of the epochs. In fact, the red and dark blue lines move nearly in parallel. And this means that during training, we converge to an increasingly sharp minimum while the model overfits. And this relationship becomes particularly clear when we plot the robust loss on the y-axis directly against the robust flatness on the x-axis. Again, higher flatness values correspond to sharper minima, and blue corresponds to the beginning of training, while red corresponds to later epochs. And robust loss and flatness show a nearly linear relationship in this plot. So this basically supports our hypothesis that overfitting is partly caused by converging to sharp minima. This can also be reproduced on a lot of different models and adversarial training variants. For example, here we consider label noise as a very simple regularization scheme and adversarial training with adversarial weight perturbations, AT-AWP, as a recent adversarial training variant. And both reduce or even prevent robust overfitting. For label noise, robust loss only increases slightly for later epochs. For AT-AWP, an increase in robust loss can be avoided altogether. And at the same time, training does not converge to very sharp minima, and this can be seen using significantly lower values on the x-axis. Also note that for AT-AWP, this also leads to lower overall robust loss on the y-axis compared to adversarial training with or without label noise. And this trend continues when considering adversarial training with additional unlabeled examples, which is a popular strategy for boosting adversarial robustness. Even flatter minima are found at the end of training, as shown using lower values on the x-axis, and similarly lower values for robust loss on the y-axis are achieved. And this also corresponds to significantly lower robust test errors, as highlighted in red. These results indicate that popular adversarial training variants improve robustness partly because they avoid sharp minima during training. In these cases, this is achieved through strong regularization, for example. This is confirmed when considering robustness and flatness across hyperparameters. Again, we show robust loss on the y-axis and flatness on the x-axis, and we highlight several selected adversarial training variants or regularization schemes in different colors. Hyperparameter settings are indicated using the shading and summarized in the legend on the right. For example, the robust test loss for traits in violet or AT-AWP in yellow depends strongly on their hyperparameters. But at the same time, better hyperparameters in terms of robust loss also correspond to flatter minima. This trend is made explicit using the colored regression lines These show a very clear relationship between improved robustness and improved flatness. Overall, this relationship also extends across different training variants. We found a very clear correlation between robustness and flatness in the robust loss landscape, as highlighted using the red regression line. This is present across a large variety of adversarial training variants, regularization schemes, and also activation functions we considered. For example, most recent adversarial training variants improve adversarial robustness, also find flatter minima in the bottom left. This includes traits as a brown circle or AT-AWP as a blue diamond. Other variants such as MART as light blue lie somewhere in between. And regularization schemes, a lot of regularization schemes are also able to find flatter minima and at the same time improve robustness. And here examples include label noise as a green circle or stronger weight decay as an orange circle. Even delaying the learning rate scale as a red circle can reduce overfitting, thereby improving flatness and robustness. Finally, we found that methods explicitly optimizing flatness, such as entropy SGD, as a yellow circle here, also improves robustness when combined with adversarial training. This relationship can be confirmed when considering the robust generalization gap on the left. This is basically quantifies the difference between test and training robust loss. And similarly, this correlation can be confirmed considering the difference between the robust loss of the last and the best epoch, which basically quantifies the benefit of early stopping. In conclusion, our paper shows a clear correlation between sharp minima and bad robustness. Vice versa, finding flat minima during training is a key for good robust generalization and avoiding robust overfitting. And this can be verified throughout training across hyperparameters and across various methods as shown here. We believe that our results shed light on how we can further boost robustness using adversarial training, and more information can again be found online in the paper.